Hello friends and welcome to another lecture on chemical engineering thermodynamics. Today we shall study about excess or residual enthalpy. Now why is excess or residual enthalpy calculated? This is Professor Arvind Prasad. Well, when we are talking about enthalpy of an ideal gas, then enthalpy here is a function of only temperature. But when we talk about real gases, then enthalpy here is a function of temperature and pressure. This is the difference between ideal gas enthalpy and real gas enthalpy. So now we take that the enthalpy of an ideal real gas is H is equal to H, that is H is the function Tp. So we differentiate it, we get dou H by dou T P dt plus dou H by dou P T dP. Now we know that dou H by dou T at P is Cp. Now Cp here is the specific heat of gas at constant pressure. Okay? So this is what it is. At constant pressure, the change in enthalpy with respect to time, with respect to temperature, is Cp. It's the specific heat of the gas at constant pressure. So we can replace that now. We can write dH is equal to Cp dt plus dou H by dou P T dP. Now from the first law, we can write the first law as du plus dPV is equal to dQ minus PdV plus VdP. Well, what I have done is du is equal to dQ minus PdV is the first law. What I have done is I have added dPV on both the sides. Now if I add dPV on both the sides, what do I get now? I will get plus V dP. This is what I will get, because minus PdV plus dPV will give you plus V dP. And now we can write this as dH is equal to T into ds plus V into dP. And this is what is the equation that I have written. Now this comes from the first law. Now if I take the temperature constant, then I can divide this entire equation by dP and take the partial differential and write it as dou H by dou P at T is equal to T dou S by dou P at T plus V. And replace this in our equation for dH, and finally we get Cp dt plus T dou S by dou P T plus V dP. Now, what we have really is, now let's take minus dG is equal to minus S dt plus V dP. Now, if this equation is exact, which we take, then from Maxwell's equations, the idea of Maxwell's equation, we get minus dou S by dou P at constant temperature T is equal to dou V by dou T at constant pressure P. Now we replace this with this and we get the following equation. So this is the Maxwell's equation. This is the idea behind the Maxwell's equation, and we replace it and we get minus V minus T dou V by dou T P T dP. So we apply the chain rule, that is dou V by dou T at P that into dou T by dou P at V plus dou P by dou V at T is equal to minus 1. And we also apply the equation dPV is equal to P into dV plus V into dP. Now where does this equation exactly come from? Well, we all know that for any fluid PV is equal to ZRT. Now, when I say fluid, it will be a liquid and a gas. Whenever you refer to the term fluid, it's actually liquid and gas. Now, at constant temperature, this is a constant. Okay, if this is a constant, we can write dPV, which is going to be equal to 0, of course, is going to be equal to P into dV plus V into dP. Okay, so this is equal to this P dV plus B into dP, right? So this is what the equation is here. Now we replace these two equations in our equation, that is Cp dt plus V minus T dou V by dou T dP. Now dP into T dou V by dou T at P, we replace using the chain rule, and V dP we replace using this equation, right? And we finally get this equation, that is dH is equal to Cp dt plus dPV, okay, into T. Then we have all this, okay. Now, since T is constant, we replace PV by ZRT. Only R is a variable, T is a constant here. So we remove T here out, and of course, R is the universal gas constant, and we remove it out here. And we get this equation. So finally, when we apply the integration, we put the limits from HR is equal to 0 to HR is equal to HR. Now, at the base condition, it is assumed that the fluid is an ideal gas. Okay. And that it is considered at, okay, when it is an ideal gas, the pressure is very, 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 very low and the temperature is, okay, whatever is the base temperature. But at that base temperature, we take the pressure as very low. So the volume tends to infinity at that point. So when the pressure is very low and the volume is tending to infinity, it's an ideal gas. For an ideal gas, HR is 0. Why? Because HR is nothing but the difference between the real gas enthalpy and the ideal gas enthalpy. Now, if the gas itself is the ideal gas at the condition of the base conditions, then you are going to have HR as equal to 0. Now, at the condition of temperature and pressure at which we want to calculate the enthalpy of the real fluid, HR is going to be equal to HR, that is the residual enthalpy. That's going to be equal to RT integral when it's an ideal gas. Obviously, for an ideal gas, we know that Z is equal to 1. So 1 to Z, V infinity to V, V infinity. The concept was already explained. And this is what we have. So finally, we have this as our equation for the residual enthalpy of a real fluid. Now, you would wonder, why do we go into the rigmarole of all this? Remember, if we have some equation for calculating the residual enthalpy, then the enthalpy of the real fluid is only equal to the residual enthalpy plus the enthalpy of the ideal gas. Now, if we have an equation to calculate this, this is already calculable using Cp into dt. So we can calculate the enthalpy at the condition which we want. That is, at any temperature and pressure, the enthalpy of the real fluid. Now, fluid models are given and they have to be put into this integral to solve it, right? So we shall look into it in problems that come in Mumbai University, and we'll try to solve them really there. Okay. Now, this was all about how to make a derivation or how to get a master equation. Now, this is the master equation. I request all of the students to at least mug up, if you like that word, or by heart if you like that word, or commit to memory is a better word. Commit to memory this equation. Now, this equation can apply to any cubic equation or state. Once again, let me remind you, this equation applies to any cubic equation or state. So therefore, this one equation can be used to derive the residual enthalpy for any cubic equation of state that you would come across into your entire career or your entire course, right? So this is the equation. Okay, so that was all about how to calculate the excess or residual enthalpy. So these are Corona times. Take care and keep watching my videos. They'll be updated as soon as I get some interesting topics, and you'll find that the updation is quite frequent. What I want you to do is subscribe my channel, and please send link of my channel to all the students of chemical engineering all over the world if possible, and to your friends, so that they subscribe it. You see, when you subscribe, it gets me motivated, and it makes all these videos, the entire motion of making all these videos a worthwhile experience. And of course, I do understand that students are getting value out of this. So once again, subscribe, like, share. That's very important. And whomsoever you share, please ask them to subscribe. Okay, friends, goodbye. Have a great day.